Hello, in this video I'm going to solve the following problem for you. The subject, electromagnetism, the topic, electrostatic force. Two positive charges, Q sub 1 and Q sub 2, are located at points 1 and 2 with position vectors r sub 1, r sub 2 respectively. Find a negative charge Q sub 3 and its position vector r sub 3 such that if it is placed there, the net force acting on each of the three charges is 0. Pause the video at this point and give it a try. Okay, let us first sketch a diagram that helps us to understand the problem better. Okay, so here I have my coordinate axis x, y, and z, and I have two positive charges. One of them is Q1 located at the point whose position vector is r sub 1, and the other positive charge Q2, which is located at the point whose position vector is r sub 2. The problem is asking for a negative charge. The magnitude of this negative charge is unknown and its location is also not unknown. But the objective of the problem is to find the magnitude of this negative charge and its location so that when you look at the combination of these three charges all together, the net force acting on charge 1 because of the presence of charges Q2 and Q3 is 0. The net force acting on charge Q2 because of the presence of charges Q1 and Q3 is 0, and finally the net force acting on charge Q3 because of the presence of charges Q1 and Q2 is 0. That is the objective of the problem. It is easily seen that the only candidate points for the location of this charge should be somewhere on this line segment joining these two charges Q1 and Q2. Let us see why is that the case. For example, assume on the contrary that we place Q3 somewhere here. Q3 is supposed to be a negative charge, so the force between Q1 and Q3 will be an attractive force, which will give a force in this direction. And the force between Q2 and Q3 will also be attractive, so it will be a force in this direction. And because these two forces are not aligned on the same line, it is not possible for the vector sum to be 0. So if I choose Q3 somewhere here, or in any other point except these points, it is not possible to make the net force acting on Q3 0. Okay. But what about, for example, if I continue this line, is it possible to locate Q3 somewhere here on this line but outside the space between Q1 and Q2? The answer is no. Because in this case, Q1 will attract this, so there will be a force in this direction, an attractive force in this direction. And because Q2 is also positive, there will be an attractive force a little bit smaller because the distance is more on this direction. So even though in this case the vectors are aligned on the same line, but both of them are pointing into the same direction. So again, the net force, the vector sum of these two vectors cannot be 0. And something similar, an argument similar to this will show that no, it is also not possible to be on the left side of this line segment as well. So the only candidate points, if possible, will be somewhere here, okay? We want to investigate if it is possible to find the magnitude of Q3 and the exact position of Q3. Okay, so first let me draw this line here for you. And by that reasoning, you realize that if it is possible to have this configuration according to the demand on the problem, Q3 should be somewhere located on this blue line segment. Where exactly it is, we have to calculate if possible. Okay, so let us, for example, just imagine that Q3 is here, and let me consider its vector position by this pink vector, which I will call it R3. So if I ask you what are the unknowns in the problem, you will tell me the magnitude of charge Q3 is unknown, and the vector R3 is also not known. What are the given ones? The given ones are Q1, Q2, R1, and R2. We know all about these things. We also know that the net force acting on each one of the charges should be individually equal to 0. Before starting solving the problem, let us try to investigate how many pieces of information are provided by the problem and how many unknowns I have in principle. Okay, first the number of unknowns. Q3, because you know electric charge is a scalar quantity, so to know the charge, you just need to know the magnitude. Okay, so Q3 is one unknown that you are looking for. In general, when you're talking about a vector in a space without any constraints, you have 3 degrees of freedom. One for the x component, the other for the y component, and the next one for the z component. So if you do not have any constraints on the vector, you will have 3 degrees of freedom. But now, according to my reasoning before coming to this, we'll realize no, in this case Q3 can just be somewhere on this line. So if I want to know this vector, I only need to know the tip of this vector, but the tip of this vector have only 1 degree of freedom, not 3 degrees of freedom. For example, if I tell you the distance of charge Q3, for example, from charge Q1, it is enough for you to immediately find this vector R3. So R3 has 1 degree of freedom now, and Q3 has 1 degree of freedom, so in total I have 2 degrees of freedom. But how many pieces of information are apparently provided for us in this problem? It seems that we have 3 pieces of information. Why is that? Because the net force acting on Q1 according to the problem should be 0. This is 1 piece of information. The net force acting on Q2 should also be 0. This is the second piece of information. And the net force acting on Q3 should also be 0. This is the third piece of information. So apparently I have 3 pieces of information available, but I only need to find 2 unknowns. So there is a discrepancy between the number of pieces of information and the number of unknowns. At the first sight, it seems that I have some redundancies, yes? I have some extra pieces of information available here. But that is not the case. Why? I want to show you that these 3 pieces of information are not 3 independent pieces of information. There are only 2 independent pieces of information, which is exactly as the number of the unknowns that I'm looking for. And the reason is that because we also have the third Newton's law. Okay, so for example, let me just clarify what I mean here. So let us concentrate on Q1. Okay, we know that the net force acting on Q1 according to the problem should be 0. So what does it mean? It means that the force exerted on charge 1 by charge 2, so let me denote it in this way. This is the force exerted on charge 1 by charge 2. Okay, plus the force exerted on charge 1 due to charge 3 is equal to 0. This is the net force acting on charge 1. And we also have the net force acting on charge 2, so it becomes 1 acting on 2 plus 3 acting on 2 should also be 0. We also know that 1 acting on 3 plus 2 acting on 3 should be 0 as well. But my claim is that one of these equations can be concluded from the other 2. So it means that we have only 2 independent pieces of information. To make it clear for you, for example, I am telling you that if this is granted and this is also granted, this one will automatically follow. To show that, let me add this equation and this equation side by side. What do I will have? I will have F21 plus F31, the left side of the first equation, plus F12 plus F32, the left side of the second equation, and on the right hand side I have 0 plus 0. But now look, according to Newton's third law, F21 plus F12 will be 0, because F21 is the force that charge 2 exerts on charge 1, and F12 is the force that charge 1 exerts on charge 2. According to Newton's third law, these two forces are equal in magnitude and opposite in direction, so the sum of these two forces will be 0. And then on the right hand side I will also have 0, so on the left I will have these two. So this will imply that F31 plus F32 will be 0. Okay, and then if I multiply both sides by a minus sign, this becomes minus F31 minus F32. On the right hand side I will have 0, but if I ask you what is F minus F31, because of the Newton's third law again, you can write it as F13 with positive sign plus F23 with positive sign equals to 0. But now look, this is what you got, and this is exactly the third equation you have. So that's what I'm saying. If you have these two equations, the third equation follows automatically. So it is not a third independent piece of information. You will have only two pieces of information. Okay, and it doesn't matter which ones you choose, because the third one will automatically follow. Okay. To save some space, if you don't mind, let me clean this. We will not need this. Okay, now let us try to solve the problem. To make writing a little bit simpler, I would use letter X to denote this distance. It's a positive number, it's distance, and I will use Y to denote this distance. Okay, let us concentrate on charge Q3. There will be an attractive force acting on Q3 because of the presence of Q1, and there will be an attractive force acting in this direction on Q3 because of the presence of Q2. My demand is that these two vectors should be equal in size. So I'm concentrating on the magnitudes. So first let us concentrate on the magnitude of this vector, and let me secondly concentrate on the magnitude of this vector. Then I have to use Coulomb's law. Okay, so the magnitude of this vector, the attraction force between Q1 and Q3, will be K, the famous constant, which is approximately 9 times 10 to power 9 in Coulomb's, with appropriate units, of course, in Coulomb's law, multiplied by the product of charges, Q1, Q3, divided by the distance between charges, which I denoted it by x squared. But be careful, I am talking about the magnitude. This cannot be a magnitude because according to the problem, Q3 is negative. So if I want to make it a magnitude, I have to make sure it's positive. So this is why I put a minus sign. This is the magnitude of the attraction force between Q1 and Q3. I equate it with the magnitude of the attraction force between Q2 and Q3. Similarly, it becomes minus K Q2 Q3 divided by, this time the distance between these two is y, so y squared. Let us do some simplifications. So minus k and minus k are gone. Q3 and Q3 is also gone. So what is left for me is simply Q1 over x squared equals to Q2 over y squared. Okay. But let us try to understand this problem. So how many unknowns you have in this equation? You see Q1 and Q2 are given in the problem. X and Y are two unknowns, but these are not independent because you can see that X plus Y in this picture is the distance between Q1 and Q2. Of course, if the location of Q1 is given using the vector R1 and the location of Q2 is given by the known vector R2, you can immediately find the distance between them. So the distance between these two is not unknown. So in principle, if I ask you what is x plus y, what is x plus y? X plus y is this distance. Okay, but now look, is this vector known to you? Yes, this is just the vector r1 minus r2, which are given. So this means that this is the magnitude of the difference of these two vectors. So x plus y is this given number. The norm, I'm using these parallel lines to show the norm of a vector, the magnitude of the vector, and it is given. Okay, but now let me go a little bit further. I take square roots from both sides, so it becomes a square root of q1 divided by x equals to square root of q2 over y. Okay, first of all, I do not put plus or minus sign because these are positive quantities. Q1 and Q2 are positive, x and y are positive, so when I take square roots, there is no need to put plus or minus. I have to keep only plus ones. The reason I did this, because I want to use this famous relation from high school studies that you have a fraction a over b is equal to c over d, okay? Then if you want to, you can add the numerators, you can add the denominators, and make a new fraction, a plus c over b plus d. It is very easily seen that this new fraction has the same value as the original fractions. It's very easy to prove this. Okay, for example, you see 1/2 is equal to 3 over 6. Both of them are equal to 0.5, yes? But if I add the numerators, becomes 4. If I add the denominators, becomes 8. Again, 4 over 8 is 0.5. So that's the content of this theorem. Okay, so this means that, let me start from here and use this theorem. So what I can write square root of q1 over x equals to square root of q2 over y equal to square root of q1 plus square root of q2. I am adding the numerators, and when I add the denominators, I will get x plus y, but x plus y is nothing except this norm, so it becomes norm of r1 minus r2. Okay, so for example, you can consider these two, and then you can find x. Okay, so this multiplied by that is equal to this multiplied by x, then you will find x. It's very simple calculation. So of course you can also find y, but let me just calculate x. So x becomes a square root of q1 divided by square root of q1 plus q2, plus square root of q2 multiplied by the norm of vector r1 minus r2. Okay, so let me keep it in the box for future reference. Okay, now let me go and calculate, so equate the other two magnitudes. Okay, so according to my previous explanations, it doesn't matter which pair you choose. For example, let us choose the force acting on Q1. There are two forces. The force acting on Q1 because of the presence of Q2 is a repulsion force because both of them are positive, and the force because of the presence of Q3 acting on Q1 is an attractive force. Again, these two should be equal in magnitude because they are already opposite in direction and they are already aligning on the same line. So the only thing I have to take care of is making the magnitudes equal. Okay, so if I consider the force between Q1 and Q2, according to Coulomb's law again, both of them are positive, so the magnitude of that force is just k times q1, q2, but the distance between q1 and q2 is nothing except x plus y squared. On the right hand side, the magnitude between the magnitude of the force between q1 and q3 will be minus, because q3 is negative and I'm talking about magnitudes, it becomes q1, q3. The distance between them squared is x squared. Okay, so let us simplify things. So this k will be simplified by this minus k, so be careful, there is a minus 1 left here, and q1 and q1 are cancelled. And then if you don't mind, instead of x plus y, I can write this norm, okay? So what happens now, this becomes q2 divided by norm of r1 minus r2 squared, and on the right hand side I will have minus q3 divided by x squared. Okay, but look, I am looking for the magnitude of charge q3. So q3 from this equation will be minus x squared divided by norm of r1 minus r2 squared multiplied by q2. Let me double check if I am right. So q3 is this x squared times q2. That's correct. Yes, that's correct. And that is exactly q3 that I am looking for. But instead of x, I can put this expression in, because it is not acceptable yet. You see, this expresses q3 in terms of q2, in terms of r1 minus r2, which are good, but x should be replaced because the only given information in the problem are q1 and q2, r1 and r2. Okay, so this motivates me to write everything in terms of these given numbers. Okay, so I have to raise this x to power 2. This will give me q1. This will give me this one squared, and this will give me this one squared. But because of this division, this will be gone. Okay, so it becomes q1. So q3 becomes minus q1 q2 divided by square root of q1 plus square root of q2 to the power of 2. That's very good. So we were able to find the magnitude of this charge. So this is the value of the charge q3, and you see that already a minus sign indicates that q3 should be negative. Okay, but now I need to find the location of r3. So how can I do that? To find r3, I add r1 and this vector together. Okay, so this vector has the magnitude x, okay, and it is in the opposite direction with respect to r1 minus r2. Okay, so I need to find a unit vector in the direction of this vector. Okay, but that's very easy. You need to divide this vector. You need to divide this vector by its magnitude. No, r1 minus r2 is in this direction, so I have to divide it the other way. So if you don't mind, let me start from here. Okay, so not make things complicated. Okay, so vector r3 is what? Is vector r2 plus y plus this vector, which is a vector whose length is y, and it is in the same direction as r1 minus r2. So first let me find a unit vector on r1 minus r2, but that's very easy. So let me call the unit vector n. I will write r1 minus r2 and divided it by its magnitude. So if I ask you what is this vector n, you simply tell me it's a vector of length 1, because it is a vector r1 minus r2 divided by its own norm. So it will be of length 1, and it will be pointing in the same direction as r1 minus r2. So in other words, if you want, this is the vector n hat somewhere if this length is 1. Okay, that's vector n. But I want to find vector y. Sorry, I want to find this blue vector here. In order to do that, I have to multiply this unit vector n by its length. So that's what I have to do. So the vector r3 is simply the vector r2 plus y times n hat. And if I calculate this, I am done. But how should I calculate this? Very simple. So instead of r2, I just put r2. Instead of y, I have to, this is x, I have to calculate y. But from this equation, you can find y. So the only difference is, instead of having q1 here, you will have q2. So that will be your y. So your y will be square root of q2 divided by square root of q1 plus square root of q2 times norm of r1 minus r2, but multiplied by n hat. But n hat is this vector that you see here, so it will be multiplied by r1 minus r2 divided by norm of r1 minus r2. Okay? Okay, so let me make it clear. Okay, now what happens? This number, whatever it is, and that number are cancelled. And then you see that I have this coefficient multiplied by r1 minus this coefficient multiplied by r2. So let me write it and simplify it one more step at least. So it becomes a square root of q2 divided by square root of q1 plus a square root of q2 multiplied by r1 plus here I have minus r2 times this plus another r2. So if you don't mind, let me factor r2 out. It will be 1 minus the square root of q2 divided by the square root of q1 plus the square root of q2 and totally multiplied by r2. Yes, but this expression can be simplified. If you can take the common denominator, it will be square root of q1 divided by square root of q1 plus square root of q2. So then finally we are done. So the vector r3 that I was looking for is a square root of q2 times r1 plus square root of q1 times r2 divided by square root of q1 plus square root of q2, and that is r3. That will be the end of this problem. Okay, so let me just explain what I did. So what I have done is just this one. You see, because this denominator and this denominator here, sorry, this and that are the same, this combination I have written here, and this combination I have written here with the same common denominator. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.